Morning, am I audible? Am I audible? Can anyone just mention in the chat box whether my voice is whether are you able to hear my voice or not? I think my voice is clear. I can, as I am also one of the participant, I can hear my voice. Okay, today I will discuss the Laplace transform and basic theorems of Laplace transform. So let us see what is meant by Laplace transform. So this Laplace transform, it is a mathematical tool which is used to convert differential equations. Okay, so what is Laplace transform? It is a mathematical tool. It is a mathematical tool which is used to convert differential equations which are in time domain. Okay, which are in time domain into algebraic equations which are in S domain. Okay, so Laplace transform is used to convert. If we have a function f, I can't write, isn't it? I can't write. If we have a function s, okay, in time domain, or which is a function of time. Okay, in simple words, can I say f is function of time. F is function of time. Try my best to not to press my cursor so hard, otherwise. Then you can convert by Laplace transform. You can convert f of t into f of s. Okay, so this f was function of time. Now this f is function of s domain. Okay, s means frequency domain. S means frequency domain. So Laplace, draw the Laplace symbol. So Laplace, this is the Laplace. Laplace of f of t will give us f of s. Okay, so Laplace of f of t, if we determine the Laplace of f of t, function f, which is in time domain, means f is function of time, then f can become function of frequency domain. Okay, f, which was the function of time, it can be converted into the function of frequency domain by taking the Laplace. So this is the Laplace symbol. So I didn't draw properly. So this is the symbol. Okay, almost symbol. This is symbol of Laplace. So by Laplace transformation, what we can do? We can convert time domain terms into frequency domain terms. That's it, in simple words. Okay, time domain terms, if we have time domain terms, they can be converted into frequency domain terms by what? By using Laplace transformation. Okay, so differential equations are converted into algebraic equations by Laplace transformation. Okay, so I think I am able to explain in a simple possible way. So what we are doing by using Laplace transformation? By using Laplace transformation, we are able to transform. What we are able to transform? We are able to transform differential equations into algebraic equations. Okay, so whenever you want algebraic equations, if you have differential equations, you can go for Laplace transformation to convert differential equations into algebraic equation. Okay, there are few theorems, okay, which will explain the Laplace transformation. Okay, why? Because these theorems will make, we want to convert what? We want to convert differential equations into algebraic equations. This conversion can be made simpler or easier by using these theorems. Okay, by using some theorems, conversion of differential equations can be made easier to transform into algebraic equations or to convert into algebraic equations. So let us see what are those theorems. So they are known as basic theorems of Laplace transformation. Okay, basic theorems of Laplace transformation. So first theorem is existence theorem. First theorem is, it's better if you people whoever have joined the session, it will be better if you write it down simultaneously as I'm explaining, so that you can remember these theorems easily. If you simply watching, then I don't think it will feed in your brain. Okay, so if you are simultaneously writing, then it will be good for you to remember for a longer period of time. So first basic theorem of Laplace transformation is existence theorem. So this existence theorem, it states that, okay, it states that for a piecewise continuous function f of t. So if you have a function f of t, and if you take the Laplace transform of f of t, okay, so this symbol I got it from the equations of the text equations. I have got, this is what the symbol I have got. You need not draw like that. You can draw like this. My cursor won't listen to me, so I will draw it. Function f of t, you can draw like this. Function f Laplace of f of t. You can draw like this. Okay. I wanted to close the bracket, I couldn't. Okay, there is an extra line here. That line you need not draw, but this is what a symbol that I got from the equations of this while writing the content. So from the symbols and equations I got that symbol, so that's why I have just copied that symbol from the equations. Okay, now if you have a function f of t, if you want to take the Laplace of f of t, okay, this Laplace of f of t will exist. It will exist if and only if is t, that is time domain, t is always greater than or equal to 0, and when you want to convert that into S domain, isn't it? And this should also be greater than t. Okay, so the existence theorem states that for a piecewise continuous function f of t, Laplace of f of t will exist if and only if time is greater than or equal to 0 and the converted Laplace transformation function S, okay, S domain is S is greater than, in S domain S is greater than t. Okay, so this is existence theorem. Let's go to the next theorem. Next theorem is first shifting theorem. Okay, first shifting theorem. So the first shifting theorem, it states that if you have a function f of t, so if I have a function f of t which is in time domain, of course it is understood that it is time domain because it is f is function of time here. Okay, if we have a function f of t which is in time domain, and if this f of t is multiplied with e power minus at, okay, if you have a function f of t and if it is multiplied with e power minus at, then in S domain, when you convert, if you take the Laplace of f of t multiplied with e power minus at, in S domain, the function will shift by an amount of a. Okay, the function that you are going to get in S domain, it will shift by an amount of a. Let us see how it happens. So Laplace of f of t multiplied with e power minus at. So if you take the Laplace of this, you will get a function f. Okay, f of s you should get, but it will be shifted by an amount of s. So you f of s plus a you must write. Okay, so if we take the Laplace of exponential term to the power of minus at multiplied with function f of t, so Laplace of that product will give us f of s plus a. This is first shifting theorem. Okay, this is first shifting theorem. So I hope you people are copying it down. Okay, so I take much more longer time to explain, so it's better if you write it down. Okay, so I hope you might have written. So let's go to the next one, second shifting theorem. So this second shifting theorem is almost similar to your first one. Okay, so here in the second shifting theorem, let us consider a unit step function. Unit step function means what? This is a step and its magnitude is 1. Okay, its magnitude is what? Unity. Okay, this is the step symbol, isn't it? Okay, so we can give step inputs, step waveform. Step input waveform, you can give step input waveform. So if you give step input waveform, so its magnitude, its length will be 1. So if the length of each step is 1, that is unit step. So if you have a unit step function, so that is unit step function is usually represented by u. Okay, and it is it converts exponential function from time domain in S domain. Means if you have a unit step function in S domain, you will get the exponential function. Okay, so if you have a unit step function in time domain, it will be converted into exponential function in S domain. So here there is an example here. Laplace of u of t minus c is there, multiplied with g of t minus c. Then in Laplace form, that is in S domain, you will get e power minus cs g of s. Okay, so e power minus cs g of s. So if we have a unit step function multiplied with some other function, okay, so u of t minus c is a function which is multiplied g of t minus c, then the Laplace of that will be given as e power minus cs into g of s. So if you have a unit step function, you will get the exponential function. That is the main concept here. So this is our second shifting theorem. Don't wait for me to ask you to write it down. You people just write it down. Don't rely on me. Okay? Don't rely on me means don't wait for me to ask you to write it down. That's what I'm telling. Okay? I hope you have written. Let us go for the next translational theorem. That is first translational theorem. Okay, this is known as first translational theorem. This theorem is applicable when if you have a function f of t and if it is multiplied with exponential term. Okay, if you have f of t and if it is multiplied with e power at and if you take the Laplace of this product, then what will happen? Let us see. So Laplace of e power at multiplied with f of t, that can be rewritten as integral of 0 to infinity e power minus s minus at f of t dt, that is equal to f of s minus a. So Laplace of e power at multiplied with f of t will give us f of s minus a. Okay, directly if you want, you can write like that. Okay, so you can even write in terms of integral. If you are multiplying exponential term with f of t, if you want to take the Laplace, that can be rewritten as integral of 0 to infinity e power minus of s minus at. Okay, f of t dt is equal to f of s minus a. So no need to write this integral part directly. You can write the Laplace term is equal to f of s minus a. So these are all the basic formulas of Laplace transformation. You have to remember these formulas. So no need to simplify or calculate while we are solving numerical problems in our which are related to electrical circuit or network analysis. When we are solving numerical problems, you have to implement these basic theorems so that again and again you need not write the integral form and you need not solve it and all. Okay, so there is no need to derive this f of s minus c again and again. Okay, now let us go to the let us continue that. So what is our Laplace? What is our term here? Laplace of product of what? E power at f of t. Okay, e power at f of t. So that can be rewritten as f of t at s tends to s minus. Okay, so Laplace of e power at multiplied with f of t can be rewritten as Laplace of f of t at s tends to s minus a. That's what is happening here, isn't it? Here, what to say? Here there was only t. Okay, only t was there, but here we have s is extended to s minus a, isn't it? S is extended to s minus a. So that's why Laplace of e power at f of t that is equal to, you can rewrite it as Laplace of f of t at s tends to s minus a. Okay, so after taking Laplace of f of t s tends to s minus a, you can write it as f of s at s tends to s minus a. Okay, so Laplace of f of t at s tends to s minus a, you can rewrite it as f of s at s tends to s minus a. That is nothing but f of s minus a. Okay, that's it. Similarly, we can take the inverse Laplace transform of this equation. Means if I have Laplace term, that is f of s minus a, if I take the inverse Laplace, what should I get? I should get this. Okay, I should get this e power at f of t. So inverse Laplace, this is the inverse Laplace, Laplace to the power of minus 1 if you write, that is known as inverse Laplace. Inverse Laplace of f of s minus a, you can write it as inverse Laplace of f of s at s minus a tends to s. Okay, inverse Laplace s minus a tends to s. So that is equal to what? E power at into f of t. Okay, so inverse Laplace means if I have s domain function, I can convert that into time domain function. That's it, nothing else. Okay, so if we have s domain function, we can convert that s domain function into time domain function. So inverse Laplace of f of s minus a, you will get e power at f of t. So in inverse Laplace, what is happening? S minus a is replaced by s. In Laplace, what is happening? S is replaced by s minus a. Okay, so that is the difference here. So just reverse. So if we are getting, if f of t, Laplace of f of t is equal to f of s, then inverse Laplace of f of s is f of t. That's it. So you will get the, okay. So if question is, if for so and so question, so and so is the answer. If so and so answer is the question, then whatever question was that will be your answer. That's it. Okay, reverse. That's it. Nothing else. So you can even convert Laplace terms into time domain terms simply by taking the inverse Laplace. So I hope you might have written. So next, second translational theorem. So in the second translational theorem, if we have a function f of t minus a and another unit step function, that is u of t minus a, and if you multiply these two functions f of t minus a and u of t minus a, and if you multiply and if you take the Laplace transform of these two multiplied terms, you will get e power minus as f of s. Okay, and similarly that's what is here. You can see here Laplace of f of t minus a u of t minus a. So whenever u is mentioned, that means that it is unit step function. Remember that u represents unit step function. So if you take the Laplace of f of t minus a multiplied with u of t minus a, then you will get e power minus as f of s. Okay. Similarly, here comma should be there. Similarly, if you have another function g of t and a unit step function u of t minus a, and if you multiply these two, you will get, okay, you will get e power as Laplace of g of t plus a. Okay, so see here, Laplace of g of t, u of t minus a, if it is there, then if you remember, I have already told you, if there is a unit step function, you will get exponential term in the Laplace form. So e power as Laplace of g of t plus a, you will get. Okay, so we don't have terms here. You may think that what is the need to write Laplace in the in S domain? We don't know the exact numerical values or terms here. If we know the terms, we can further simplify. Okay, we can further simplify this function. Okay, now we are just learning the theorems, that's it. So in a second translational theorem, if f of t minus a is multiplied with u of t minus a, and if you take the Laplace transform of that, you will get e power minus a as f of s. And if you have a function g of t multiplied with the unit step function u of t minus a, if you take the Laplace of that, you will get e power minus a as Laplace of g of t plus a. Okay. So now, if you have if you have the Laplace transformation value, that is e power minus a as f of s, and if you want the time domain, you just take the inverse Laplace. If you take the inverse Laplace, you will get f of t minus a, u of t minus a. That's it. So inverse Laplace. Okay, if you want the time domain values, if you have S domain, if you want the time domain, you must go for inverse Laplace. If you go for inverse Laplace of e power minus a s f of s is equal to f of t minus a, u of t minus a. Okay, so let's go for the next one. Initial value theorem. This is more important when compared to all the theorems. This is the theorem. That is applicable in many of the numerical problems. So initial value theorem. So let us consider function x of t. Shall I change the ink? Like yellow one. Let us consider x of t. So if you take the Laplace of x of t, you must get x of s. Okay. So this is it. According to initial value theorem, if you have x of t, and if you take the Laplace of x of t, if you take the Laplace of x of t, you will get x of s. Here LT means Laplace transformation. Okay. So if we have x of t, if you take the Laplace of x of t, okay, the cursor is not listening to me. If you take the Laplace of x of t, you will get x of s. Okay, so if we have x of t limit with the limit x t tends to 0, with limit t tends to 0, if you have x of t with limit t tends to 0, okay, if you have x of t with limit t tends to 0, I will take some other color, that will be equal to x of 0. Then in Laplace form, okay, in Laplace form, isn't it? T tends to 0 means what? Limit of x of t, limit t tends to 0 means what? Nothing but x. It is nothing but x of 0. Instead of t, you must write 0. So x of 0 will be equal to limit s tends to infinity s x of s. Okay. limit s tends to infinity s x of s in Laplace form. So according to initial value theorem, if you have limit t tends to 0 x of t, then in Laplace form it will be converted into limit s tends to infinity s x of s. Okay. So no need to write theory and all. You better write the skeleton part, that is the equations. Okay, you just write the equations. No need to write the whole theory. Next, final value theorem. Okay, final value theorem. So if we have x of t, it can be converted into x of s by Laplace transformation. That's what I have written here. Is here you have x of t, Laplace transform. I will write the Laplace symbol. I will try my best to write the Laplace symbol. So Laplace of x of t. Laplace of x of t, you will get x of s. So limit t tends to infinity x of t. So here t tends to infinity, is x of infinity is equal to what? Limit s tends to 0 s x of s. So Laplace of, here I didn't write the Laplace symbol, you can write the Laplace symbol, the Laplace. Okay, Laplace of limit t tends to infinity x of t. Okay, Laplace of can't write bracket, even bracket. So Laplace of limit t tends to infinity x of t is equal to what? Limit s tends to 0 s x of s. Okay, this is the final value theorem. So initial value theorem and final value theorem are important. So I hope I might have written this. Few more theorems are there. We'll discuss and conclude this concept. Next, superposition theorem. Okay, so if we have some constant a1 and another constant a2, then if these constants are multiplied with functions, a1 is multiplied with f1 function, f1 of t, and a2 constant is multiplied with f2 of t, then if you take the Laplace of this, Laplace of a1 into f of t, f1 of t plus a2 into f2 of t, then the Laplace of this will give us a1 f1 of s plus a2 f2 of s. Okay, it's very simple. So it's better, let me take red and write the Laplace symbol. I didn't write Laplace symbol here. You can write the Laplace symbol. So Laplace of a1 f1 of t plus a2 f2 of t will give you a1 f1 of s plus a2 f2 of s. Superposition theorem is simple. Similarly, complex shifting theorem. So if you have a constant which is greater than 0, okay, the constant is a. So a is nothing but our arbitrary constant. Okay, so which is the power of exponential term. And if you take the Laplace of e power minus at f of t, means exponential term with the arbitrary constant as power multiplied with f of t function will give us f of s plus e. Okay, this is complex shifting theorem. So I hope you might have copied. Let's go to the next one. That is similarity theorem. Similarity theorem. So in this theorem, let us once again consider an arbitrary constant a. which is greater than 0. Okay, and if it is in the function, if it is multiplied with t, then take the Laplace of the function f of at. Laplace of function f of at will give us 1 by a f of s minus 1 by a f of s by a. Okay, so Laplace of f of at, where a is a arbitrary constant which is greater than 0, then Laplace of f of at will give us 1 by a f of s by a. Okay, that is our similarity theorem. One more theorem is the derivative theorem. Okay, so if you have a function f of t, where t is greater than 0, and if you take the derivative of f of t, that is d by dt of f of t, and if you take the Laplace transform of this d by dt of f of t, you will get s f of s minus f of 0 plus. Okay, so f of 0 plus means, remember that it is the initial time. Okay, so immediately when switch is closed, immediately after closing the switch, that time is our 0 plus time. Okay, so Laplace of the derivative of f of t, where t is greater than 0, will give us s f of s minus f of 0 plus. Okay, next, integral theorem. Integral theorem. So if we have function with its integral, and if you want to take the Laplace transform of that function, so Laplace of the integral function, see, Laplace of integral 0 to t f of tau d tau. Okay, will give us, if you take the Laplace of this term, you will get 1 by s f of s. Okay, it's very simple. So if you have a function which has an integral, so integral of 0 to t f of tau d tau, if it is there, okay, then Laplace of that is given as 1 by s f of s. Okay, next one, complex differential theorem. Sorry, it's differentiation theorem, not differential. So complex differentiation theorem. So in the complex differentiation theorem, if we have time t which is multiplied with function f of t, here it is, see, t multiplied with f of t, the power of t can be any value. Okay, so some constant, let us assume k is some constant. So, and if you take the Laplace of this, so I will write the Laplace here. I will write the Laplace here. Okay, I succeeded to write the Laplace. So Laplace of t to the power of k is a constant, t is time, multiplied with function f of t, then the Laplace of that is given as minus 1 to the power of k d to the power of k by ds k and ds to the power of k f of s. Okay, so this is complex differentiation theorem. So complex differentiation theorem is what? Laplace of t power k f of t is equal to minus 1 to the power of k into d to the power of k by ds to the power of k into f of s. And differentiation of f of s multiplied with minus 1 to the power of k. It seems no one is there in this session. Okay, I have received many good morning messages, but only, no? Good morning for what? What is the need of this good morning if the concurrent viewers are not there? Okay, no concurrent viewers, but good morning is there. What I am going to do with that good morning? What is the need of the good morning? Okay, you don't know the value of education. No interest, it's okay. No interest, no studies. Okay, convolution in the time domain. So if you have two functions, f1 of t and f2 of t, and if you multiply these two, and if you take the Laplace of these two functions, f1 of t and f2 of t, this is the last, what to say, this is our last basic theorem. Okay, so if you have two functions, f1 of t and f2 of t, if they are multiplied, if you take the Laplace of this product, you will get integral of 0 to t f1 of tau f2 of t minus tau d tau. You can rewrite like this, and in Laplace form you will get f1 of s into f2 of s. That's it. Okay, in the Laplace form you will get f1 of s into f2 of s. That's it. I hope you might have written. Okay then. So I'm going to close this session, and immediately I will start another session with another topic. So I want to mix all the topics in one session. So I want to segregate the sessions topic wise. So I'm going to conclude this session. Okay, you people just leave and rejoin the another session.